Okay, I don't know why I'm having so many problems this course with the computer. Maybe I'll have somebody look at it. But the next 7 lectures are on basics from atomic structure and bonding to crystal structures to phase diagrams. So that gives us the basics for all the refractory compositions. So today we have electronic configuration, which is atomic structure and a little bit on the periodic table. And then the types of bonding. There's atomic and molecular orbitals, metallic bonding, ionic, covalent, intermediate, and van der Waals. So it turns out most of the high temperature ceramics and refractories are ionic and covalently bonded, or more commonly, a combination of ionic and covalent bonding or intermediate bonding. So a real simplified atom is just a positively charged nucleus, and there's a nucleus is surrounded by the negatively charged electrons. A nucleus consists of protons and neutrons. The protons are charged +1 and neutrons are neutral. And the nucleus is surrounded by electrons or an electron cloud, and that determines the types of chemical reactions that can take place. So atoms can gain or lose electrons during a chemical reaction. They form positive and negatively charged ions. A positively charged ion is a cation. A negatively charged ion is an anion. That would be more or less ionic bonding. Atoms can also share electrons during a chemical reaction. That would more or less be covalent bonding. Just a few more definitions. Isotopes are atoms with the same number of protons, but different numbers of neutrons. And if it's electrically neutral, the number of protons are going to be equal to the number of electrons. So the electron energies are quantized. There's discrete energy levels. And these energy levels or values are going to increase with increasing distance from the nucleus. And there's an exclusion principle. No 2 electrons can occupy the same state, but electrons can move from one energy level to another. So the nucleus contains the protons and neutrons. That's where most of the mass is concentrated. So if we look at the mass of electrons, protons, and neutrons, an electron only weighs 9.11 times 10 to the minus 28 grams. It has a -1 charge. And then the protons and neutrons are almost the same. This is 1.67 times 10 to the minus 24 and 1.68 times 10 to the minus 24. A proton has a +1 charge and a neutron is neutral. So the electrons are arranged in quantum shells. So they're located in specific shells or levels. And the energy depends on the location in the shell. So there's a principal quantum number for each shell, n equals 1, 2, or 3, and so on, 4, and so on. And then the number of electrons in each quantum shell is 2n squared. So for the first level, n equals 1. N squared would be 1 squared. 1 times 2 is just 2 electrons. For the second level, n equals 2. N squared is 4 times 2 is 8 electrons. For the third level, n equals 3. N squared is 9 times 2 is 18 electrons. And then for n equals 4, 4 squared is 16 times 2 is 32 electrons. So these are the principal quantum numbers, n, 1, 2, 3, and 4, and they contain 2, 8, 18, and 32 electrons. Each quantum shell or level is divided into subshells, and these subshells contain electron pairs. and each electron pair has an opposite magnetic spin. So we decided the number of electrons in the shell is 2n squared. So for n equals 1, there's 2 electrons, and those 2 electrons are in an s suborbital. N equals 2, there's 8 electrons. The first 2 electrons go into an s suborbital, and then 6 additional electrons go into the p suborbital. For n equals 3, where there are 18 electrons, we start out with 2 in the s orbital, 6 in the p orbital, and then 10 in the d suborbital. And then finally, for n equals 4, 32 electrons, 2 in the s orbital, 6 in the p orbital, 10 in the d orbital, and now there's an f orbital with 14 electrons. So this is a schematic representation. The nucleus is the dot in the center. N equals 1 is the first shell. And in that shell are 2 electrons in the 1s level. N equals 2 is the next level. And there's a 2s containing 2 electrons. And then the 2p suborbital contains 6 electrons. And then finally, n equals 3 has the 3s, 3p, and 3d suborbitals. S has 2 electrons, p has 6 electrons, and d has 10. So this is a very simple representation of the subshells. They're not quite like this in reality. So we need to have a notation to describe these electrons. So this notation really helps us decide which electrons can be added or removed when bonding takes place. So this example is magnesium, Mg. It has 12 electrons. So 1 is the quantum shell, S is the subshell, and then the exponent here is the total number of electrons in each subshell. So in the first quantum shell, there's the s suborbital with 2 electrons. In the next quantum shell 2, there's 2 electrons in the s suborbital, 6 electrons in the p suborbital, and then the third quantum shell, there's 2 electrons in the s orbital. So in an atom like magnesium, the third quantum shell with these 2 s electrons are the ones that are responsible for chemical reactions. So this is what magnesium would look like in this simple representation. The nucleus is in the center. We have your first quantum level 1 with 2 s electrons. The second quantum level 2 has 2 s electrons, 6 p electrons, and then this third quantum level has 2 s electrons, and those are the ones that provide bonding during reactions. Another example is oxygen. Oxygen has 8 electrons. So the first quantum shell with the s suborbital has 2 electrons, and then the second quantum shell has 2 s electrons, and now only 4 p electrons. So there's 2 electrons basically missing from this p subshell. So in order to, when a reaction takes place, perhaps you're forming MgO, the Mg atom gives its two outermost electrons, and then the oxygen wants to basically wants to complete the p level and have 6 electrons. So it is taking the 2 electrons off of the Mg atom. So that's a very good example of ionic bonding. Iron has 26 electrons. This is a last example I have. So all of these levels are filled. 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. D should have 10 electrons to have a complete level, but it only has 6. And then the 4s level has 2 electrons. It is filled. So 4s actually fills before the 3d level. So this is a transition metal. So this is these two levels, 3d6 and 4s2, are the ones that are responsible for chemical bonding. So if you just take out the outermost electron levels that are responsible for bonding and properties, you write it in this form, 3d6, 4s2. That's an abbreviated notation. So if you look at the periodic table for all the elements, this table just shows the abbreviated notation for the outermost electrons, which are responsible for bonding. So here's magnesium. We just looked at that one. 2p6, 3s2. These are the outermost electrons. Iron, 3d6, 4s2. And then finally oxygen, 2s2, 2p4. So all of the electrons in the outermost level and in this abbreviated notation like this are shown on this periodic table. So the way these shells are filled, we have 1s all the way up to 8s, 2p to 7p, 3d to 6d, and 4f to 5f. So 1s is filled first, the 2s electrons, and then 2s is filled next, 2 electrons. Then we start with 2p, that's 6 electrons, and then back to 3s. And now that the level 2 is filled, and then we go to 3p, 6p electrons, to 4s, the 2 electrons. And then next is 3d, which is another 6 electrons. So now we have the third level filled. And then we go to 4p, and then finally 5s. And then we go back to 4d, 5p, and 6s. And then we start filling in F level, 4f, 5d, 6p, and 7s. And then finally another F level, 5, 6d, 7p, and 8s. So they don't necessarily fill in exact order. So this is a diagram of these different levels, 1s all the way up to 4d. Each bar represents a subshell that has 2 electrons. So the first shell, number 1, is also called the K shell. So that's where n equals 1. The second shell, 2, is also known as the L shell for n equals 2. And the third one here, number 3, n equals 3, is also known as the M shell. And then the fourth one here, n equals 4, is also known as the N shell. So this is the order in which they fill 1s, 2 electrons, and that level 2s, 2 electrons, 2p. So there's 2 electrons in each one of these bars. So that's a total of 6. Then we go to 3s, 2 electrons, 2p, 6 electrons, again, 2 in each bar. And then instead of going to 3d, we go to 4s, 2 electrons, and then finally 3d, the 10 electrons here. Then we skip the 4p, 6 electrons, and finally 4d, 10 more electrons. And how that works, we can look at iron again, which has 26 electrons. So there's an arrow up and an arrow down. Each arrow represents an electron. The arrows in different directions are the different spin directions. So we have 2 in the 1s, 2 in the 2p, 2 in the 2s, and then 6 in the 2p. Again, 2 in the 3s, 6 in 2p, 2 in the 4s. And then the 3D, we feel like in this order, each one of these shells, suborbital shells, fills with an electron. Then we go back to the beginning, and now this one has a second electron. So there are 1, 2, 3, 4 orbitals here that only have 1 electron. So this is a transition metal, and this is the reactive shell that causes bonding. So I've shown a couple of the rows in the periodic table here. This is row 1. We have hydrogen and helium, and we just fill a 1s, and then the second 1s electron. So highlighted in red is helium because it's got a complete outer shell that's filled, and it's an inert gas. So the second row goes from lithium to beryllium to boron, carbon, nitrogen, oxygen, fluorine, and neon. So the 1s is already filled. The 2s is filled after beryllium, and then from boron to neon, the 2p level fills. And again, neon has a complete set of electrons in its shell, so it is an inert gas. And the third row starts with sodium, then magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. So the 1s, 2s, and 2p shells are completely filled, and after magnesium, the 3s is filled, and then from aluminum to argon, we fill the 3p level, and argon, again, is an inert gas. All the shells are filled. And then the last row I show here starts with potassium and calcium, and then from scandium to zinc, that's the transition metal: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. So from 1s all the way up to 3p, all the levels are filled. We fill the 4s level before the 3d level with potassium and calcium. Then from scandium to zinc, we fill the 3d level. Those are the transition elements. And then the rest of row 4 goes from gallium to krypton, gallium, germanium, arsenic, selenium, and bromine, and finally krypton. And after germanium, the 4s is filled, and then we're just filling the 4p level. So finally we reach krypton. So all the levels are filled here again. Krypton is inert. It's an inert gas also. So the periodic table is just a graphical display of what's known as the periodic law. And in this periodic law, it's just basically saying properties of the elements exhibit a periodic dependence on their atomic number, where they're located in that table. So the rows are known as periods. The columns are known as groups. So in a row, the non-metallic character increases as you go from left to right. And then in a column, the elements in adjacent columns exhibit similar chemical characteristics. So on this periodic table here, I show the suborbitals. This is S, P, and D. That's the transition elements. And then elements 57 through 71 and 89 through 103, those are the F suborbitals. On this table, the atomic numbers are shown. For example, beryllium, the atomic number is 4. The atomic mass is also shown. Here's boron, 10.881. So the atomic number is simply the number of proteins in the nucleus of an atom, or it's the number of electrons if the atom is neutral. If it's neutral, a number of protons equals the number of electrons. So the atomic mass that's shown on the periodic table is actually the weight of 6.022 times 10 to the 23 atoms, or if you have a molecule, it's the weight of the molecule. This number is Avogadro's number. It's known as one mole. So 6.022 times 10 to the 23 atoms make up 1 mole of an atom or a molecule. So if we look at carbon, 1 mole of carbon contains this Avogadro's number of atoms, and it equals 12.001 grams. Magnesium, 1 mole of magnesium equals 24.305 grams, and it contains an Avogadro's number of atoms. So the valence electrons are what's important for the different chemical reactions and compound formation. So an electron in the outer shell is associated with an atom that can participate in the formation of a chemical bond if the outer shell is not complete. So these are the electrons that are available for bonding, the valence electrons. So if we go back to the periodic table, 1, 2, 3 through 12, and then 13 through 16 are the groups. And then the rows go 1, 2, 3, 4, 5, 6, 7. So we're looking at the groups. So group 1 has 1 valence electron. Group 2 has 2 valence electrons. And then we skip over to group 13, which is over here. We're just not looking at the transition elements. So group 13 has 3 valence electrons, 14 has 4, 15 has 5, 16 has 6, 17 has 7, and group 18 are the inert gases. They actually have 8 valence electrons, but in reality they have 0 because they're inert. They have a complete outer shell that's filled. So we can look at 2 refractory materials, MgO and Al2O3. So this is the electron notation for Mg plus 2 and O minus 2. So Mg has these 2 valence electrons that can take place in chemical reactions, and O minus 2 actually has 6 valence electrons. They're highlighted in red. So 3s2 is for Mg, and O is 2s2, 2p4. So when you form MgO, these 2 electrons in this S3s orbital end up in this 2p orbital of O2. So this becomes basically 0, and this is p to the 6th. So that'd be s to the 0, I guess. So then you have an Mg plus ion and an O minus 2 ion. So that's an example of another ionic bond. And Al2O3, Al plus 3 and O minus 2. 3s2 and 3p1 are the 3 valence electrons that can react. And oxygen, again, has 6 valence electrons, 2s2 and 2p4. So each aluminum atom gives up 3 electrons and becomes a plus 3 cation. So it gives up these 3 electrons, and each oxygen gains 2 electrons. So to balance the charges, there's 2 Al atoms at plus 3, so 2 times 3 is 6, and 3 oxygen atoms at minus 2, 3 times minus 2 is 6. So that forms a compound Al2O3. So Al plus 3 is a cation, O2 again is the anion. This is just a simple table illustrating basically the same thing. it's not complete. It starts out with hydrogen, helium, then the next row is lithium, neon, the next row goes from sodium to argon, and the next row is actually potassium to krypton. And then in the lighter, more gray notation here, those is just showing the outer electrons that are responsible for the chemical reactions. So these valence electrons are the electrons that determine the properties, chemical properties, the electrical properties, thermal properties, and optical and magnetic properties. So I put down a few more charts here that show some of the trends in the periodic table. And the first one here is for atomic radius, the size of the atom. And the size of the atom is going to vary depending on the charge. So this table is atomic radius in picometers from 0 to 300, and then atomic number from 0 to 100. There is no 0, it starts at 1. And this is lithium, sodium, potassium, rubidium, and cesium. These are the rows in the periodic table starting with these elements. So as you go across a row, that would be in the downward direction here, the size decreases from left to right across the row. And then in this direction, the size increases going down a column. Size increases going down a column. So a column would be lithium, sodium, potassium, rubidium, and cesium. You can see the size increasing in that direction. So the atomic radius is important because when we talk about crystal structures, how the atoms pack in the crystal structures is going to be a function of their size. This is just the periodic table. It's kind of a schematic diagram of the sizes of the different elements. So you can see going down a column, the size is increasing, and then going across a row, the size is decreasing, and then you finally get to the inert gases where there's an increase in the size again. The transition elements in the center here, they're pretty constant in diameter because you're filling the inner shell, a D-level shell. So their size is relatively constant as you're filling inner shells in these transition elements. So cations versus anions. And a cation, you're removing an electron. So when you remove an electron, the atomic radius decreases. And anions, when you gain an electron, the size actually increases. Maybe there's some questions here. Correct. I kept this in here, and I did say this one becomes 0, but yeah, that is correct. So Mg has 3 s2 electrons, and Mg plus 2 is missing those 2 electrons. So here's how they change. So oxygen, for example, when it's neutral, its radius is 0.066 nanometers. And then when it gains 2 electrons, it gets bigger. So it's O minus 2. So it becomes 0.14 nanometers. So it becomes larger. Mg is 0.16 nanometers. And then when it loses 2 electrons, it becomes Mg plus 2. It decreases in size 0.065. And Another example might be calcium. It starts out at 0.197, and then Ca plus 2, losing 2 electrons, it decreases to 0.099 nanometers. So the atomic radius changes as the oxidation state of these elements change. Again, that's important for building crystal structures. And a couple other points here. Ionization energy, that's the energy required to remove an electron. And it's in ionization energy is in electron volts versus atomic number. 1 electron volt just equals 1.6 times 10 to the 19 joules. So here's lithium to neon, sodium to argon. These are the rows, potassium to krypton, and so on. So the rows are shown here. So the ionization energy increases from left to right across the row. So it's more difficult to remove an electron going across the row from left to right. And then the ionization energy also increases as you go up a column. And then another concept which is useful for determining the ionic character is the electron affinity, and that's the energy release when adding an electron to an atom. So electron affinity versus atomic number. Electron affinity is in electron volts, and lithium to fluorine, sodium, chlorine are the rows again. So the electron affinity increases going up a column. So the higher the electron affinity, the higher the ability of an element to acquire an electron. So fluorine and chlorine have high electron affinities. They want to become fluorine -1 and chlorine -1. Elements with low electron affinity, like lithium and sodium, they want to give up an electron and become lithium +1 and sodium +1. So this is another periodic table just showing the electronegativities. So electronegativity is simply the degree to which an atom tends to gain electrons that form negative ions in chemical reactions. So fluorine, oxygen, chlorine up in this corner of the periodic table, the electronegativities are greater than 3. And on this side of the periodic table, the electron negativity is less than 1. Cesium is 0.79, sodium is 0.98. So electronegativity increases going up a column, and electronegativity increases from left to right across the row. Now, there's atomic orbitals and molecular orbitals. So for atomic orbitals, the electron configurations for individual atoms represent their lowest energy states. But now for molecular orbitals, when 2 or more atoms bond together, their electron configurations change, and for a reaction to take place, there will be a lowering of the energy state. So if we look at a simple example, 2 hydrogen atoms, they both have a 1s electron configuration. They'll combine to form hydrogen H2. So here's an individual hydrogen, actually 2 hydrogen atoms with their atomic orbitals. And if they form H2, they're going to form a molecular orbital MO. And this is going to be a lower energy configuration. If they do not form a compound, it's anti-bonding. That's because the energy is higher for this state than for the individual atomic states. So if we look at the energy here, this is energy in this direction. This is an atomic orbital for one hydrogen atom, 1s. This is an atomic orbital for a second hydrogen atom in the 1s state. And this is where bonding takes place with a lower energy level, and that's forming a molecular orbital. So in that case, each one of these 1s electrons are shared between two hydrogen atoms, and that's basically forming a molecular orbital. And an anti-bonding situation here is not possible because you would have to go to a higher energy state. So carbon is an important element for refractories, and we'll look at an example for graphite. Carbon is 1s2, 2s2, and then 2px1, 2py1. So we can call the three p suborbitals to distinguish them x, y, and then z. So what happens when we form graphite? We form a hybrid sp2 bond. So we have a 1s2 orbital, and now we have a 2s1 orbital. One of these electrons is going to go into this other orbital, pz. So one of these electrons from the 2s orbital goes into a 2pz orbital. So now there's one electron in each p suborbital. So that's a hybrid sp2 bond. So bonding takes place between one s orbital and two p orbitals. And now we form a triangular unit with 120-degree angles between these bonds. So each carbon atom is bonded to three other carbon atoms, and they're triangular units. So they're going to form a two-dimensional planar structure. So graphite is basically a two-dimensional planar structure. We'll talk about these structures in more detail when we get to the different crystal structures. So the 3pz electron molecular orbital is only half filled when you form this hybrid sp2 bond. So here's your 2s level, and your 2px and your 2py levels, and they're forming this three levels, 2px1, 2py1, and 2pz1. So there's three sp2 orbitals. And I have a better picture here. These orbitals that are at 120 degrees, and basically that's how the bonding takes place in graphite. You have these hexagonal arrangements of carbon in these layered structures. And the hexagonal arrangement will have 120-degree angles. So they're forming an sp2 hybrid orbital. And then carbon also forms diamond. And that's a hybrid sp3 or sp3 bond. So now the S1, you have an S1 orbital, one electron goes into this pz orbital. But now bonding takes place between one s orbital and all three p orbitals. So now you're forming tetrahedral units, and they have angles of 109.5 degrees between the bonds. So now each carbon atom is bonded to four other carbon atoms. Back in graphite, they're only bonded to three other carbon atoms, forming a two-dimensional structure. But in diamond, they're bonded to four other carbon atoms, forming a three-dimensional network structure. That's why diamond is a very hard material. So all the bonding electrons are now in molecular orbits. So in terms of a diagram, you have your 2s level, you have your 2px, 2py and 2pz levels, and they're forming these 4 hybrid orbitals. You can see the 4 orbitals here, 4 sp3 orbitals. And again, a better diagram shows this angle at 109.5 degrees. So these are forming a 3-dimensional units with tetrahedral units making up the entire diamond structure. Oh, we're not that interested in metallic bonding in this course, but I'll just mention it. In a metallic bond, there's just a mutual attraction of all the nuclei in the structure to a cloud of shared valence electrons. So the electrostatic repulsion of these negatively charged electrons keeps their distribution uniform. So basically each atom, they're sharing electrons in this electron cloud. So each atom always has enough electrons around it to satisfy an outer shell that's filled. So metallic bonding occurs in elements to the left and to the interior of the periodic table. So the alkali metals such as sodium and potassium are bonded by their outer s electrons. And because they're the outer s electrons and their low atomic number, they have low bond energy. So these are low melting materials. But the transition metals such as chromium, iron, and tungsten are bonded by their inner electrons in the d level. So they have high bond energy and much higher melting temperatures. So you have these nuclei sitting in an electron cloud. So the atoms are going to form these close packed structures, pretty simple close packed structures. And there's really 2 types here, a hexagonal structure and a cubic structure. So the open circles are close packed atoms. So that would be 1 layer. We'll call it the A layer. And then the next layer would be the B layer. These are the dark circles. So you can see this B layer fits into these interstitial openings on this A layer. And then for forming a hexagonal unit, the next layer, or the 3rd layer, is again an A layer. So that layer, the 3rd layer, is fitting exactly over the 1st layer. So the stacking is A, B, and so on. For the cubic structure, we have 3 layers, A, B, and C. So our A layer, and then our B layer is the same as for hexagonal. It's fitting in these interstitial voids. But now the C layer is fitting in these interstitial voids over the B layer, and the C layer is not coinciding with the original bottom A layer. It's in a different location. So now we have a stacking sequence, ABC, and that forms this cubic structure. So because of this close packing, these structures are quite simple. In an ionic bond, 1 atom is giving up 1 or more electrons to another atom, and these atoms accept these electrons. That it maintains electrical neutrality and achieves stable filled electron shells. And we looked at MgO and Al2O3 as examples. Another example is NaCl. So Na is 1s, 2s2, 2p6, 3s. And chlorine is 1s2, 2s2, 2p6, 3s2, and 3p5. So there's 1 s electron here that is easily given up, and this one needs 1 electron in the p level here, the completed shell. So there's an electron transfer. This 1 electron in this 3s level is transferred to complete this 3p5 level, which is now 3p6. So chlorine has a complete outer level, and that's shown here. So now we have an Na plus ion with 11 protons and electrons, so it has a +1 charge. And chlorine Cl minus, has 17 protons and an extra electron, 18 electrons, so it's a negatively charged ion. So this ion is positive, this is negative. They held together by Coulombic attraction. So the plus and negative charge ions attract each other. So that's a good example of ionic bonding. So when we talk about crystal structures, it's determined by two factors: the number of atoms of each element required to maintain electrical neutrality, and then the optimum packing is based on ionic size. So the size of these ions determine the coordination number, and the coordination number is simply the number of nearest neighbors, whether it's an atom or an ion, surrounding an atom or an ion. So in our crystal structures for ionic materials, the anions, the negatively charged ions, are positioned in a closed packed arrangement. And then the cations, the positively charged ions, fit between the anions in the interstitial positions. And those interstitial positions are near the sides of the cation. So the large open circles are the anions, the black circle is the cation. So when a cation just fills an interstitial position here, it's the most stable. And if it's a little bit bigger, it's still stable. But when it's much smaller, it's not a stable configuration. So the way these ions are packed is going to determine what kind of crystal structures result. So if the cation to anion ratio is small, 0.155 to about 0.225, the coordination number is going to be 3. So there's going to be 3 anions surrounding one cation. If this ratio is between 0.225 and 0.414, so the cation is a little bigger, it's going to take 4 anions to surround that cation. So the coordination number is now 4. And then going up in size in a higher ratio, 0.414 to 0.732. Now the coordination number is 6. 6 anions surround the cation. And then if the ratio is greater than 0.732, the coordination number is now 8. So you can see as the ratio of the anions to cations changes, the coordination number changes, and that's going to dictate the type of crystal structure. Ionic bonding is non-directional if it's pure ionic bonding. And directional bonding, when there's some degree of non-ionic bonding, you have some directional bonding. Non-directional bonding is just packing of the anions and then filling the interstitial sites with the cations. So there's a degree of ionic character, and we can estimate that degree of ionic character from the electronegativity scale. So I showed a periodic table with the electronegativity numbers on it, but this is a electronegativity on the X scale here, going from 0 to 4. And then these are the atoms in their different columns. So lithium to cesium is the first column. So these are all less than 1. So on the left-hand side of the periodic table, there's a low affinity for electrons. But on the right-hand side, the column starting with fluorine, ending up with iodine, has a high affinity for electrons. So they're up around 3 or even higher. So the degree of ionic character of whatever compound that forms can be estimated from this electronegativity scale. So the larger the electronegativity difference between the atoms, the larger the degree of ionic character. So if the electronegativity difference is greater than 2, you pretty much have an ionic compound with plus and minus anions and cations. If the electronegativity difference is between 0.5 and 1.6, now you're having some covalent character showing up, and you have some unequal sharing of electrons. And if the electronegativity difference is small, 0 to about 0.5, you have covalent bonding and you have an equal sharing of electrons. So this is a plot of fractional ionic character going from 0 to 1 or 0 to 100%, and then the difference in electronegativity going from 0 to 3. So as you go up with higher in the electronegativity difference, you're increasing the ionic character. So the larger the electronegativity difference between atoms, the larger the degree of ionic character. And likewise, the smaller the electronegativity difference, the larger the covalent character. So +1 ions in group 1, the first column in the periodic table, lithium, sodium, potassium, and so on. And the -1 ions in group 17, which is fluorine, chlorine, and bromine, they produce highly ionic compounds because they have a high electronegativity difference. These tend to have low strengths and low melting temperatures. Now, the higher charged ions, which are of interest to us in making refractories, Mg+2, Al+3, and Cr+4, and oxygen O-2, these are much higher charges. They also produce ionic compounds, but because of the higher charge and the greater bond strength, they're going to have high strengths and high melting temperatures. In a covalent bond, 2 or more atoms share electrons, and they're now achieving stable filled electron shells. Whereas in ionic bonding, you're packing the anions and in a close packed arrangement, fill the interstices with the cations. It's not a directional bond, but when you're sharing electrons in a covalent bond, the bond becomes directional. So it's not like metallic bonding and ionic bonding, where you're packing the atoms in a close packed array. Directional bonds, covalent bonds, are also high strength and high melting temperatures. These are materials like silicon carbide and silicon nitride. So an example of a simple covalent bond is O2, a diatomic gas. 2 oxygen atoms share 2 electrons. So the nucleus is the open circle and the black dots are the electrons. So they're sharing these 2 electrons. So now in the outer orbital, they have 8 electrons. So each orbital is complete. But the bonds are directional. So covalent bonding occurs between atoms of similar electronegativity. They're not close in electronic structure to the inert gas configuration. So atoms of intermediate electronegativity, carbon, nitrogen, silicon, germanium, tellurium, these form highly covalent structures. So silicon and carbon is a highly covalent structure when you form silicon carbide. So because they're directional, they're not close packed structures. They're 3-dimensional structures. They're not tightly packed. So they're going to, because they're directional, they're going to have cavities in their crystal structures. The intermediate bond is a bond between ionic and covalent character. And this is the case for most of the materials that we're going to deal with. So MgO, if you look up the electronegativity values, E and Mg minus EO is 2.3. And if you look on that chart, the table I showed for ionic character, it's about 75% ionic. SiO2, ESI minus EO is 1.7. That's about 50% ionic character. Silicon nitride, ESI minus EN is about 1.2 or 0.3 or 30% ionic character. Then silicon carbide, ESI minus EC is only 0.3. And on that chart, that comes out to 0.03 ionic character. So this is essentially covalently bonded. And then a material like carbon in the diamond structure, EC minus EC has to be 0. So it is completely a covalent bonded material. So MgO, SiO2, silicon nitride, silicon carbide, and carbon are all important refractory materials. And then the last type of bonding is van der Waals bonding. These are weak secondary bonds, basically fluctuating electric dipoles lead to weak forces of attraction. That's known as dispersion. Or you can have electric dipoles that form in asymmetrical molecules. That leads also to weak forces of attraction. That's known as molecular polarization. So van der Waals bonding is also important in layered structures, and in refractories we have to deal with clays, graphite, boron nitride. And we'll go over these structures in detail when we talk about these raw materials. But in clays and graphite, in the layers, there's very strong bonding, but between the layers, there's very weak van der Waals bonding. So the properties, when we talk about properties of materials, are directional. So graphite will have very strong bonding in the layered structures, and that'll lead to directional properties like thermal expansion will be very low. But between the layers, perpendicular to the layers, weak bonding will give very high thermal expansion. So properties will be very much directional in these materials because of the difference in bonding. So that's the last slide that I have on bonding. And I guess next week we'll spend 2 days on all the crystal structures and see how the structures are put together, what kind of rules for forming the structures. And these will be the structures for all the different kinds of ceramic or refractory materials that we need to know about. So thanks for listening in today. Have a good weekend, and I'll see you next Monday.